Another type of discrete random variable distribution that we might run into that is very useful is our binomial distribution. Okay, so binomial distributions, they are still discrete random variables, but the outcomes and some of the requirements are a little bit different than we've talked about before. Okay, so in our binomial situation, the outcomes are defined as either successes or failures. Okay, so we can take a whole lot of scenarios and transform them into a binomial situation. For example, we could talk about something like basketball players at the free throw line. One thing that we could say is that, he took 15 shots at the free throw line. How many, did he make? And so the successes would be like whether he made a basket or whether he failed at making the basket. And we would then count to see like how many he actually made. So that's like one example. We could even transform our dice example. Previously we had for our outcomes for a dice example of like the numbers 1 through 6. And that would be the probability that, on a given dice roll, any of those possible outcomes would happen. Well, what if instead we were talking about like rolling the dice 6 times and we wanted to know the probability of rolling 3 or more heads? Well, binomial lets us figure out how to answer that because we are defining our outcomes as successes or failures. And the outcomes then are just the number of successes out of a fixed number of trials. All right, so for a binomial, we need a little bit more information than just this, but our outcomes are defined as successes and failures. So here's what we need. The first thing that we kind of need is we need to know the number of trials. We have to know in our specific scenario, how many times are we going to roll the dice? How many times is somebody going to shoot free throws? How many times? We have to know the number of trials. The other thing that we need to know is we need to know the probability of success for a single trial. So we need to either collect some data or know, like with a specific dice roll, like if we're talking about, rolling the number 1 over and over again, we need to know what's the probability of success for just one trial. Once we have that probability of success, then we can actually build kind of one of those probability tables with our PMF and our CDF. But we need these two things. Now, tangent or connected to this is that we also need to kind of have a few rules with our binomial distribution. And like one of the rules that we need, just like kind of with our outcomes are defined as successes and failures, is that we need the trials to be independent from one another. This is important so that our probability of success doesn't go changing on us. We need that the probability of success for a single trial, we need that probability to be the same for every single trial in our particular experiment. So trials need to be independent from one another. If not, we can't really use this binomial situation. Okay, so there is a way that we can calculate out like these probabilities of success. And so let's just talk about if we were doing, shooting free throws. It's a good example. So let's say we're shooting free throws. And I know that when I step to the free throw line, maybe I'm something like a 60% shooter. Okay, so we know that the probability of making free throw is equal to 60%. And let's say that I'm going to shoot the basketball 5 times. So we'd say number of trials is equal to 5. And we can label that as n. Okay, so we've got a number of free throws. We've got our probability of success. We've got these things as defined as successes or failures, so we could make it or not make it. And then the trials will be independent. So we have to assume that you making or missing a shot ultimately really doesn't affect your next shot. Now you might argue with me whether or not that's actually true, but for this scenario, we're going to assume that it is. Okay, so now let's kind of start building our probability table. So we know that X, once again, is all possible outcomes from our scenario. And you might want to just quickly throw up 1 through 5 because we're shooting the basketball 5 times. But we'd be making a mistake because in this scenario with binomial, is it possible that I miss all 5 of my free throws? And the answer is absolutely. So that is a possible outcome. 0, I could make 0 out of my 5 free throws. Totally possible. What about, is it possible to only make 1? The answer is yes. 2, 3, 4, and 5. Now, is it possible to make 6 shots out of 5 free throws? The answer is no. So now I have a complete support. Those are all of my possible outcomes from my binomial scenario where I am shooting free throws. Okay, so now that I've got my support all set up, now we have to start talking about building our PMF, or our probability mass function. And we need some tools. We actually need an equation to help define what these probabilities equal. Now the rules still apply. Those probabilities still need to be between 0 and 1 inclusive. And when we sum them all up, they need to add to 1. And we're like, well, I don't really know what's the probability of doing 2 free throws out of 5. And like I said, there's an equation. It's kind of ugly, it's a little bit big, and we're actually going to use software most of the time to tackle it, but I do want to show you what the equation actually is. And here we go. So the equation for our probability mass function is going to be equal to, we're going to start off by doing what's called a combination. So we're going to be using some factorials. So it's going to be n factorial divided by, and then it's going to be x factorial. And remember, x is our outcome, so that'd be the number of successes that we've got. And we're going to do n minus x factorial. Okay, but that's just the first part. And then we have the variable pi. It stands for the proportion or the probability of success. So this probability of success is for a single trial. That is going to be equal to our pi. And this guy, we're going to have that be equal to our n. All right, we're almost there. We're going to raise this guy to the power of x. And then we're going to do 1 minus pi, or we could also say pi complement, right? Because that's what that is, 1 minus pi. And we raise this to the power of n minus x. And there's our equation for our probability mass function. Oops, got a mistake right there. For a probability mass function for a binomial distribution. And you're like, holy cow, I mean, I barely remember what factorials are. Remember, so like 3 factorial is going to be like 1 times 2 times 3. It's kind of like what a factorial is. But because of our software, we're actually just going to use our software to calculate this so that we don't have to do this by hand. Because like, what happens, I mean, this is a pretty simple scenario, but what happens if we were standing at the free throw line for 100 shots? Could we? Absolutely. Do we actually want to calculate all these by hand, you know, for like 101 possible outcomes? Answer is no, it'd take a lot of time. So I'm actually not going to fill that part out here. I'll save that for our software demonstration about how we can use software to fill out that part of the table. But just know that what it is this is the probability of success, or the probability that any one of these particular outcomes occurs, where pi is just going to be the probability of a single success, which is this guy, pi. And with these guys, with the number of trials and the probability of a single success, we can kick out the probability of any one of these particular outcomes to occur. And then we could go on and do our CDF, right? As soon as we have our PMF, we can just, you know, do this addition and do our CDF. But then we're like, we've got to go ahead and figure out our expected value and our variance. And you're like, oh gosh, there's probably, you know, a whole bunch more stuff to do. And the answer is actually really easy with our binomial situation. So in a binomial, if we want to calculate out the expected value, it's actually really easy. So the expected value, remember, once again, this is mu, is just going to be equal to the number of trials that we have multiplied by its probability of success. That's it. Super easy equation. We just take number of trials, multiply it by our pi. Remember, this is not the, like, you know, calculating out circle stuff of 3.14, not that pi. This is representing the probability of success for a single trial, the true probability of success for a single trial, and we use pi. Okay, so that gets you the expected value. Super easy, multiplying 2 variables together. So let's talk about the variance. The variance must be much more complicated. And the answer is, you know what? It's not. It's not actually that much more complicated at all. So if we want to do our variance, which is going to be equal to sigma squared, all we have to do, it's going to be n times pi complement. That's it. You just have to multiply one more thing. Now remember, pi complement, so basically it's the probability of failure. So if this guy is pi, then the probability of failure is just equal to 1 minus pi. That's it. That gets us our complement. And that is how we get our variance. And if we want the standard deviation, right, which is just equal to sigma, again, it's just equal to the square root of whatever we get for the variance of x. Okay, so a binomial situation is really quite simple to be able to go through and calculate out some of these things that we want to know, like the expected value and the variance. Now, actually building this table, it's a little bit more tricky, especially if we use the baseline equation. That takes a little bit of time. But if we use our software actually has a lot of these distributions already programmed in. And so if that's the case, we can use our software to actually build these probability tables so that we can ask, like, what's the probability of, me shooting 2 or more baskets out of 5? And I can figure out that probability from building this table and using some of these other tools. So anyhow, that is like our introduction into our binomial distribution.